Most of the time on our show, when we talk about experiments, we tell you about experiments that already exist and the results and new scientific knowledge that those experiments have brought us. However, today on our show, we are talking about an experiment that doesn't yet exist, a new kind of particle collider that many in the particle physics field are eager to build for the very first time. Instead of colliding things like protons or electrons, all that stuff we've seen before, these new particle colliders would collide muons, the heavier cousin of the electron. So why are people so excited about muon colliders, and what exactly would they do for us that we don't get with the Large Hadron Collider and all the other colliders we already have? To explain this to us, we have a special guest, Cari Cesarotti, who's going to give us everything that we need to know about muon colliders.
This episode of Why This Universe is supported by Wondrium. Wondrium offers thousands of video and audio courses on a huge range of topics. I've been listening to Wondrium for years and have enjoyed courses on everything from philosophy and history to literature, math, and science. Some years ago, I actually recorded a series of lectures for Wondrium on the subject of what Einstein got wrong. So you can go a lot of places and find out about all the great accomplishments Einstein made in his career, but here I tried to kind of turn the tables on history and focus on some of his mistakes and blunders. So if you want to learn more about Einstein and physics or just about anything else, check out Wondrium and give them a try. You can sign up for Wondrium now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. Particle colliders are perhaps our single most important tool for understanding our universe's laws, including the forms that matter and energy can take, and how those forms of matter and energy behave. We've talked a lot before on Why This Universe about particle colliders, and especially the Large Hadron Collider, the LHC, which is the current most powerful particle accelerator in the world today. The LHC collides protons together in an effort to create particles that we haven't seen before and otherwise study the interactions of exotic forms of matter. Proton colliders work great in a lot of different ways, but it turns out that they have some limitations too. With this in mind, today we're going to talk about the future and the possibility that one day we can build a machine that collides not protons together, but muons. Just thinking about the prospect of having a working muon collider gives me goosebumps. To help us with this discussion, we have with us on the podcast today Cari Cesarotti. Cari is a postdoctoral fellow at the Center for Theoretical Physics at MIT, and before that she was a PhD student at Harvard and a research fellow at CERN. She's an expert on using particle colliders and other experiments to search for new particles and otherwise test new theories of high-energy physics. Welcome, Cari, to Why This Universe.
Thanks so much for having me. It's great to be here.
Yeah, it's great to have you. Maybe just as a starter question, can you tell us a little bit about yourself and what you work on, what makes you tick scientifically?
Yeah, absolutely. So I kind of came into the particle physics scene when this really fun narrative was going on that the LHC didn't immediately find supersymmetry as soon as we turned it on. So particle physics is dead was my big welcome into the field. But I didn't care because QFT seemed fun and surely particle physics wasn't totally dead, right? So my whole career as I've kind of gone through learning about the state of the field and what we can do with it is that particle physics is emphatically not dead. There's a lot of really interesting, exciting avenues that we just haven't explored yet. So kind of the center of my research program is to figure out how we can dig out these hints of beyond the standard model physics without having an extremely dedicated, super focused program. How can we look broadly for any kind of signature of new physics? And so this kind of translates to looking for high energy things, looking for weakly coupled things, and really just looking for things that we haven't looked for before.
So maybe in some past generation, particle physicists might have said, well, I'm going to, put my money on this particular theory. Maybe it's supersymmetry or something, and you're going to do specific supersymmetry oriented studies and whatever. You're trying to maybe be a little more agnostic about the underlying physics you're looking for, but try to kind of look for a broad range of signatures of new stuff, new particles, new forces, etc. Is that a good summary?
Absolutely.
Cool.
For sure. Yeah. And I think agnostic is absolutely the right word because, again, the goal is to look everywhere that we can and not particularly in a specific model direction.
So I think you're very representative of physicists in your kind of age cohort. When I was in grad school, people really did pick their specific favorite theory and double and triple down on it, whether it be supersymmetry or some sort of grand unified theory or whatever. That is just completely different today. People are much more open-minded and much less confident that they can in advance figure out what nature is going to do.
Which is a little more fun, right? Like if we knew all the answers, why would we be looking so hard?
Would you go so far as to say that maybe in the past the field was a little bit more driven by the theorists, but maybe now it's a little bit more driven by the experiments?
Yeah, so that's an interesting way of phrasing it. And the story that I like to bring in is that for so much of history in this field in particular too, is that we kind of traded off which side is driving discovery more. So theory versus experiment, like way back in the early 1900s when Paul Dirac was hypothesizing the positron, right? He predicted a particle that wasn't out there, and that was borderline sacrilegious at the time. And everyone was really upset about this, and it led to a lot of bonkers theories, like the whole electron sea, which, spoilers, is not actually a correct theory of nature. But it was this really interesting trade-off between going back and forth from experimentalists found a particle, what the heck is this? And theorists being like, oh, this is what this particle is. We expect these other things. And so there's just kind of this, like this trade-off that happens between theorists and experimentalists of who sort of has the wheel about discovery. And so I think certainly we are in this regime where experimentalists might be looking for hints, and certainly theorists, I do think it's our job to help educate where we can find these things in a more motivated way. Don't just turn on the collider and be like, is that a new particle? Like that's not, it's not quite that simple, right? But absolutely, I think that now is the time where we should use theoretical tools to motivate where we look in colliders. And then whatever the collider gives us, then that gives us some direction. And that's where we can really zero in.
It's clear that without theorists, experimentalists wouldn't get very far. And without experimentalists, theorists wouldn't get anywhere at all. Right? The two have to work, in conjunction.
It's a physical science at the end of the day, right? Like our goal, the thing that gets us out of bed in the morning is understanding the natural world. And if there's no data, it's a fun math exercise. But to me, to feel like it's physics, you want to see that bump show up in that plot.
So we're going to talk about muon colliders today, but before we take that leap, Cari, can you maybe just kind of summarize for our listeners the kind of colliders we have working today and maybe the kind that we've used in the past, and maybe tell us something about the various strengths and weaknesses that come with the different kind of strategies we've taken.
Yeah, absolutely. So we're at a really interesting junction of particle physics experiments because usually we've had at least two colliders, either both running or being built while the other one's running. Right now we only have the one. So the one collider that we have going right now is the big fancy one that maybe we've all heard of that's in CERN near Geneva. And that's the LHC, which is the Large Hadron Collider. So the hadrons that they are colliding are protons most of the time. Sometimes they also do runs with heavy ions that they collide, like lead ions. But for the most part, what we're doing is we're accelerating protons to within a fraction of the speed of light. So we accelerate them up to about 7 TeV each, or 14 TeV total center of mass energy. We smash them together and we see what comes out. And this experiment has been remarkably successful at determining things that we already know. So it was awesome at discovering the Higgs, and that's exactly what we built this for. So the LHC was the Higgs boson machine, and it did it.
Are you of the opinion that we knew the Higgs was going to be there before we found it?
I mean, we found the Higgs when I don't mean to date myself or anyone else, but we found the Higgs like right as I was starting to be a physicist. So to me, it felt pretty cemented in that this was going to be there. But I understand that might be a bit of a cultural aspect.
Well, I agree with you on that because I can prove it. I wrote a book before the LHC turned on in which I said I thought it was 99% likely that the Higgs exists and that the LHC would be able to find it.
Yeah.
So, maybe not everybody was as confident as that, but like a lot of us were pretty sure going into it that the LHC was going to be there. I mean, that the Higgs was going to be there. Yeah. Good. So let's step back. And okay, so we've got the LHC. It's a big circular machine accelerating protons and smashing them together. What are some of the other colliders we've built and operated in the past, and how are they different from the LHC?
Yeah, so the previous one that had a little bit of runtime overlap with the LHC was the Tevatron, which I'm sure sits near and dear in your heart because it is at Fermilab.
It was in my backyard, yeah.
Yeah.
I would go jogging around the Tevatron ring, not infrequently.
Casual. Yeah, so the Tevatron was interesting because it didn't collide proton-proton. Instead, it was colliding proton-antiproton and at a lower energy. So in theory, this machine could have also discovered the Higgs, but in practice, since we had the LHC up and running, we sort of moved scientific efforts to that machine instead.
There are a lot of Fermilab people who would like to claim they did see the Higgs, but definitely not at the level that you'd claim discovery. But there was some evidence of the Higgs there.
But you guys discovered the top.
We did. We discovered the top in 1994, top quark in 1994, something like that.
Yeah. So I mean, still a very cool particle discovery. I'm not gonna polarize our audience about if the top quark or the Higgs boson is more interesting, but they're both very cool, guys. Trust me. So the Tevatron did some awesome stuff, and it was active until about 2011, which was like a couple years overlap with the LHC, I think, and the Higgs was discovered in 2012. So, we were close.
Yep.
But yeah, so the Tevatron, big difference is that was colliding protons and antiprotons versus the LHC, which is proton-proton.
And are there clear advantages to doing proton-proton versus proton-antiproton?
I mean, there's definitely different physics that you can probe. So protons are really fascinating particles because they have all these other particles inside of them. And they sort of share the total energy. So a proton might have, the 7 TeV, but inside are all these other quarks and gluons that share some fraction of that total energy with different weights. So in a proton, basically it's made out of 2 ups and a down quark and then a bunch of gluons. And an antiproton has those antiparticles. So if you're looking for things that are being smashed together with a quark antiquark, maybe there's some advantage at the Tevatron. If you're looking for gluon fusion processes, maybe the LHC has more of an advantage. So there's certainly going to be different fundamental physics that you're sensitive to based off of the constituents of your beam. And of course, an antiproton is negatively charged. So if you're colliding things and you want charged neutral objects, that makes much more sense. If you don't care about that stuff, there's all kinds of trade-offs that you're making. And this is why people like me are employed, because figuring out, what the theoretical advantage of these machines are is non-trivial and really interesting.
Okay, so we've got the LHC, which is colliding protons together. We've got the Tevatron, which in its day collided protons and antiprotons together. What other things have we collided together in the past in these machines?
So probably the thing that is, in some units, most comparable to a Muon collider is the LEP, or the Large Electron Positron Collider. And this was also at CERN. And this machine collided electrons together, or electrons and anti-electrons together. So completely different, right? Like protons are made out of gluons and stuff. Electrons are just that, they're electrons, they're fundamental particles.
Yeah, the electrons are simple and clean, right?
They're simple and clean. And clean is an awesome word because when you smash composite objects together, you get all this residue from the stuff that's just kind of a bystander in the collision, but still sprays all over your detectors and can muddle up your data. But when you have electrons, these are clean little particles. And to a lot more precision exactly what's going on. So kind of the way that people like to classify these colliders is that these lepton machines, these fundamental particle colliders, are precision machines. And then the hadron colliders are like the energy frontier, because LEP was getting at, like a factor of 50 less energy than what we can see at the LHC.
On the one hand, we can use these clean, easy to understand electron-positron collisions, but you can't accelerate those particles to very high energy because they're so light. On the other hand, we could collide protons or antiprotons together at much higher energies, but they're messy. So there's kind of a trade-off between these two things. And this sets us up now for the new kind of particle accelerator collider that you're going to advocate for, in which we collide muons. So tell our audience what a muon is and why you think it's a good particle to start colliding together.
Yeah, a muon in this world that we've just set up between this precision energy frontier is kind of the best of both worlds particle. So a muon is basically a heavy electron in the sense that it has basically all the same quantum numbers. So it has the same spin, the same electric charge. It couples similarly to things like W and Z bosons. And it's very clean. It's a fundamental particle, so there's not all this other crap in this cloud around the actual particle that you're going to be doing the collision with. So yeah, a muon is basically a heavy electron, the electron's heavy cousin.
So if we could get a bunch of muons together, we could accelerate them to high energies because they're a lot heavier than electrons, but they'd be a lot cleaner than protons because they're fundamental particles. But of course, it's hard to get a bunch of muons together. Like I can pick up any object on my desk right now and it's full of protons and electrons. It's a lot harder to find a big chunk of muon matter, right? So, what's involved with that?
Yeah, so this is really depending on who's asking, $10 billion question, which is how do we get a muon beam? Exactly like you said, Dan, like there's protons, there's electrons everywhere. These things aren't hard to find, and they're certainly not hard to produce and isolate. But muons have this really pesky property that they decay. So what that means in practice is that there are no muons natural in nature, right? Because protons, neutrons, and electrons all have effectively infinite lifetimes. And I know people are going to be like, neutrons have 15-minute lifetime. It's like, chill out, nerd. Okay. But protons, neutrons, and electrons can form stable bound objects, which we all know and love, and we call them atoms, and they make up everything. And the reason that we don't have atoms made out of muons is because they decay. So the lifetime of a muon in its rest frame is about 2 microseconds. So 10 to the minus 6 seconds, and then it's gone. And it leaves behind it an electron and 2 neutrinos. So, it's really hard to, like you said, make matter out of these objects because they're not long for this world.
So if we want to build a machine that accelerates a beam of muons, we have to create those muons and then accelerate them and collide them all in the tiny little bit of time before they decay, right? That's the challenge.
Yeah, you can't do things on the microsecond timescale.
I can personally do very few things on the microsecond timescale, but maybe the machine you're envisioning could.
Well, we all have different skills. But yeah, so this is exactly the issue, right? Is that creating muons and accelerating them up and colliding them has to happen ridiculously fast. So it doesn't all have to happen exactly in the microsecond timescale because we know from Lorentz boosts and relativity that if you accelerate something to near the speed of light, you can actually stretch out its lifetime. And this is something that muons have actually shown us really concretely in nature without colliders, right? Is that if we have these cosmic wind particles hitting our atmosphere, we still see muons survive to the surface of the Earth because their lifetime has been stretched out because they're traveling so close to the speed of light. So we don't have infinite time, that's for sure. But we have a little bit more than a microsecond to try to get these things up to energy and to collide.
All right, so Cari, like when you and others imagine a future muon collider, like what kind of machine are you picturing? Like, tell me about its size and its shape, and like where would you put it? Like, where would you envision this machine being, and what do you expect it to look like?
Yeah, excellent question. So again, these are the things that we are deciding as we go. I think what's really fun about the Muon Collider is, as a scientist, is that you actually get to see how the collider sausage is made, right? Like nothing is set in stone, nothing's been for sure decided. So it is a lot of moving parts and people optimizing. It is a lot of people optimizing the kind of lattice is what we call it. I've learned so many nice words now. The lattice of the accelerator to understand what the peak efficiency of this machine would be. So to kind of give you a virtual tour to go through what our Muon Collider might look like. The first thing that we need is protons, which is great because as per our previous discussion, we have a lot of ways of
all sorts of protons.
Protons are everywhere, basically. So step one is you get a dedicated proton beam. And the numbers that people love to give are in megawatts, which is amazing to me because as a physicist, like 10 years in the field, I've never heard someone describe things in megawatts. But yeah, so like, let's say you have maybe a 10 megawatt dedicated proton beam. And the protons need to be kind of high energy, but not super high energy. So the number that people throw around as the optimal number is about 8 GeV.
I mean, these protons are still moving at, roughly close to the speed of light, but by particle physics standards, they're not that energetic.
Exactly. Yeah. So the idea is that we take this proton beam and then we slam it into some dense material target. So the energy of the protons is kind of this Goldilocks zone of it's energetic enough to actually, have the scattering process and produce somewhat reasonable energy byproducts, but not so energetic that the beam just plows right on through the material and nothing happens. So step one is our proton beam smashes into a material target. Step two is in this interaction, there's a bunch of QCD stuff going on, and ultimately they produce this big amount of pions, which are the lightest meson particles. So those are an up and an anti-down or something like that.
A couple of quarks bound together, right? Yeah.
Exactly. And these things also want to decay quite quickly. And these things can often decay into muons. So it'll produce a muon and a neutrino pair. And that's where we get our muons.
All right. So
so it's this tertiary particle.
We take these kind of modest energy, high energy, but not that high energy protons, smash them into some matter.
Yep.
Out come some pions. The pions decay into muons. There we go. We've got our muon beam.
So yeah, that's already feels like a bit of a endeavor, but this is in theory the easy part. So that's how we get our muons. Then what we have to do is cool them. So this seems counterproductive, right? Because the whole goal is to accelerate them. But the problem is when the muons come out and these pions decay into muons, the muons have momentum in all kinds of directions. They have all different kinds of momentum. And to really create an efficient beam where we collide things into each other and things happen, they don't just whiz past each other. We need these particles to all be behaving in roughly the exact same way. So the spread and uncertainty of what momentum a particle has, the physical cross-section of what the beam needs to be super small. So after we produce the muons, step one is to cool them, and then we accelerate them. So cooling is also a big challenge of the muon collider.
There's a lot of talks about muon cooling these days. Yeah.
Yes. And I think it's really, I have, of course, enormous respect for the accelerator people, but I do love kind of the juxtaposition of like the fancy words they use and the very like blunt tactics that they have. So it'll be like, oh, this is 6D cooling, cool in 6 dimensions. You're like, oh my goodness, I thought there were only 4. And of course, they mean the 3 dimensions of momentum and 3 dimensions of space. But, we have the, futuristic 6D cooling. And then how we do it is we just slam it into another material. And, you put stuff through a material and it goes slower. And doing that, but educated, is how we cool.
When we talk about the 6D cooling, that's just a fancy way of saying you want all the muons to be really close in each other in space, like traveling very close proximity to each other, and all moving at the same speed in the same direction, right? Yeah, exactly. That's what you need to do.
Exactly.
Right. All right, so we've got our muons. We've cooled them into a beam. What kind of ring or whatever do you picture moving these muons around, and what energy do you think you could accelerate them?
Yeah, so the energy that we can accelerate muons to are why this is really an exciting prospect for, I think, a lot of corners of physics and not just particle people. So the idea is that we have kind of a bigger ring to actually accelerate them up to, because again, the tighter radius that you have, sort of the more synchrotron losses that you expect. So basically having a bigger ring means that you can have, slightly less powerful magnetic, you can have slightly less powerful magnets along the way. So we have this big accelerator ring, and then we have a slightly smaller ring that we actually run the collisions on. So we're not circulating these muons in the same ring that we're colliding them in. It's a 2-stage thing.
I didn't realize that. Okay.
Yeah, and so once we put the muons from the bigger accelerator ring into the collision ring, basically they can go around maybe 100 times. We expect there to be roughly 2 experiments of collision points where we try to actually collapse the beams and see what comes out. And then after they go around enough, the beam's decayed, we're done with it, and then we just do it again.
Well, how big? Give me numbers. Like how big is the big ring and how big is the small ring?
Yeah, so I think, they shouldn't be remarkably different in magnitude, but kind of the numbers that we put around are 5 kilometers to 10 kilometers.
Okay, all right.
Which is much more compact than what we talk about, certainly for other future colliders, but also at the LHC.
So this is a lot smaller than the ring at the LHC, but maybe comparable to like the old Tevatron ring.
Yeah, exactly.
Why separate into 2 rings? Is it just to make sure the experiments are cleaner?
Yeah, so I think, again, I'm not an accelerator person, but this is what I think is, I think that, it is a little bit easier to accelerate things on a less tight radius. Because muons decay, we can talk about this more later, but because muons are decaying so much, there's just this constant spray of high energy electrons everywhere. So yeah, it does kind of clog up your machinery sometimes to have this huge beam induced background all the time. But that is another real experimental and engineering challenge that we have to face.
Right. So it's like we have a lifetime for the muon, but really that's a statistical thing. They're kind of always decaying at random times, especially when we have so many
absolutely.
of them. And so there's all these, decay products that are, you're saying, clogging up the machine. Okay.
Yeah, exactly. That's exactly right.
So we have in mind this idea we're going to build this, mini kilometer set of rings. We're going to accelerate these incredibly high power beams of muons, and we're going to smash them together. We're going to have sensitivity to all sorts of particles that we can't see at the LHC, all sorts of laws of physics we can measure and study, all this stuff. So, of course, to do this, though, we need somebody to pay for it. And first, let's live in a fairy tale land and say let's say Congress or some billionaire or something wrote you a check for this today. Can we just start building this? Are all the problems more or less solved, or what has to happen if you had funding between now and the day you start doing physics to make this happen?
Yeah. So again, excellent question. And to respond to this, I'm going to use the phrase that we always like to throw around within our collaboration, and that is there are no showstoppers identified. So what that means is that there's nothing fundamental that we think would make this an impossible endeavor. So to give you an example of what would be impossible, or I think impossible, is to accelerate taus, because taus live even another million times less than muons. So accelerating something in 10 to the minus 13 seconds to the speed of light, that's a challenge that I don't think humanity can tackle. Prove me wrong, though. Come on.
You can deal with a microsecond or two, but you can't deal with a million times shorter than that. Okay.
Yeah, exactly. So that's kind of an example of this is fundamentally more or less impossible to do. But with a muon collider, we don't think that there's anything that would really put this project completely in the impossible regime. So that being said, there are certainly challenges that we need to overcome. So if you were going to write me a check tomorrow, I can give you the number that I think a muon collider would cost, which is, about 10 to $20 billion, which, I mean, Twitter costs more than that. So come on. But if I were going to be responsible with your money, and I advocate all of us are these days, what I would want is about $500 million, because really what we should do first is really test all of the engineering facilities that we haven't yet done. So what that includes is certainly this demonstration of a 60 cooling, because we've never had to do this before, so we never have a full scale. There's a really cool program that was run in the early 2010s called MICE, the Muon ionization cooling experiment. And they began to show some of the proof of concept studies that we need for this cooling technology to work. But of course, we didn't do it all the way up at 10 TeV, which is where we want to put muons, right? So we need to demonstrate that our understanding of cooling of these particles is correct. We also need to, test some of the magnet lattice for the accelerator. But the metaphor that I like to use is you don't run a marathon before you run a marathon, right? So we can't build a muon collider as a proof of concept of building a muon collider. So really, I think the responsible thing that we as a community can ask for is just let us show that there's nothing surprising about these kind of facilities, the cooling and acceleration. And then we can really go for it. So 500 million is what I want.
So to use your metaphor a little farther, take it a little farther, so what you're asking for, what this community is asking for, is the money it would take to start training for the marathon, with every expectation that, you're physically capable and you with enough training will be able to run that marathon. But you need to start training, and that's going to take some time and take some resources. But you think you can get there in a reasonable amount of time.
Yes.
Good.
Absolutely.
And what's that reasonable amount of time? Let's say, things go pretty well, plausible, but about as well as you might hope for. When can we hope to have this machine working?
So in again, this world where money is no object and everyone cooperates and things are ready to shovel to earth tomorrow, The timeline could be about 2045. So about 25 years is kind of an optimistic but technically limited timescale. So assuming that everything kind of goes as we expect, 25 years is not an unreasonable amount of time to expect this thing to start taking data at 3 TeV.
I'm personally looking forward to watching all the results of this in my retirement. It's going to be great. And
yeah.
Just again, sunscreen and kale, Dan. That's the secret to seeing the 10 TeV frontier.
There we go.
I think we mentioned this, but I do kind of want to go into a bit more detail about what would you expect this kind of muon collider to see that the LHC couldn't, and what's the kind of energy differential? How much more energetic would these collisions be at the muon collider? Yeah,
so this is an awesome question, and I think one that's not immediately obvious why a muon collider would be such a big difference. So kind of nominally, the energy stages that we talk about is maybe first doing a run at 3 TeV and then doing another run at 10 TeV. And then just to compare what kind of energies it is, a Higgs boson is about 0.1 TeV. So going to things 30 times, 100 times more energetic than the Higgs boson. So the number that I gave you for the LHC is about 14 TeV, but that number is again a bit misleading for what the actual fundamental physics process is. So again, these protons are composite objects. So all of the quarks and gluons inside the proton carry only a fraction of that total energy. So the energy that's available to us when we collide particles is really going to be something closer to 1 or 2 TeV, maybe 3 TeV tops. 3 TeV isn't insane, even for theories like supersymmetry, which again, we've really hitched our wagon to in the particle physics community. These things you just couldn't really see at the LHC. Because if you're not creating enough energy in your collisions to produce these particles, it's extremely hard to see a clear signal that this particle was ever produced. So once you start having a dedicated 3 TeV muon on muon, all of that energy is yours to use. So all of the energy of the muons can be cannibalized and resorted into all these different new particles. And you can really just start to see beyond this energy frontier that we've explored so far with the LHC. So going back to sort of my dog in this race about where can we find new physics, just higher energy, right? Like there's nothing magical about the energy scales that we've been able to probe so far. And there's nothing that suggests that's all the particles we have. So if you just want to look beyond, right? If you want to pull yourself up over the wall, the muon collider is really the fastest way to get up and beyond that sort of 3 TeV threshold that is really being seen at the LHC. And then just one more thing about energies at muon colliders that's really cool. Again, our staging options right now, we kind of talk about a 3 TeV and a 10 TeV. The 3 TeV number is what we give for like this 25-year timescale. But really, there's been no sort of theoretical showstopper identified to prevent this kind of technology expanded to maybe a bigger accelerator, a bigger accelerating ring, to go all the way up to 100 TeV. So really, if you want to see into the energy frontier, muons are the way to do it.
Wow, 100 TeV muon collider.
That'd be pretty cool, eh?
Yeah, that'd be amazing.
So that's the energy reason. Maybe one more reason about why this is so different from the LHC. So in the particle physics, we kind of organize our particles into generations. So the first generation is the lightest stuff. So for the lepton, the lightest lepton is the electron and its corresponding electron neutrino. Then the next heavier generation is the muon. So in theory, we expect a lot of the things that we've already seen with the standard model of particle physics, all of the category or the catalog of things that we've already discovered. So in particle physics, we like to talk about coupling as basically how strongly particles interact. But we also talk about coupling for basically describing the probability that if you try to collide some things, what's the probability that they'll collide? Basically, electrons and muons kind of couple to standard model particles in roughly the same way. And we call this universality, is that the coupling is universal depending on the generation that you look at. However, if you start to say that maybe universality isn't correct, and maybe for new physics, things couple more strongly to second and third generation stuff, that would be almost invisible at machines like the LHC and LEP and the Tevatron. So if you have these kind of theories that suggest that the coupling gets stronger to the higher generations, which isn't insane. This is how mass hierarchies work.
We already know this is true for the Higgs boson, right?
Yeah, exactly. So what is mass but the coupling of a particle to the Higgs boson? So we have evidence that this kind of hierarchy and coupling structure exists in nature. So if you think about other models that this could happen, where the coupling happens again to second and third primarily, this would be a completely unexplored region of new models that we could look for. So again, in this mentality of how can we do the most new things, higher energy is awesome. And the second generation stuff has truly never been seen before. So the novelty that you would get there is something that's just unattainable at something like the LHC or other kind of future colliders that don't look at second generation particles.
So, Cari, if I were to survey a group of particle physicists, would I find that most of them are supportive of this idea of building a muon collider? Or do they have other ideas about the kinds of experiments they might want to build in the future?
So it really depends on what demographics of people you ask. So I think if you ask people kind of my age, like early career scientists, postdocs, young faculty, things like this, people are super excited about a muon collider. And I think that makes sense as the demographic to listen to, because again, this thing will come online perhaps during our careers, if not even a little bit later. So the fact that young people are excited about it should really signal to the community that this is something worth investing in. However, if you ask maybe some of the older members of the community, they've been hurt before. I think there's a lot of emotional baggage that goes into the discussion of a muon collider, because people were actually really excited about this idea from the last, big meeting of physicists to talk about where our budget and priority should go. So we decided that a muon collider was great. We started working on it. There was the Muon Accelerator Program, or MAP, which came out of it. There was MICE, which I mentioned earlier, which also came out of it. And then got canceled. So, me not having that, love and lost feeling can definitely dive in and be like, this is awesome. We should totally do this. But certainly a lot of people who are still experts in it today have this kind of heartbreak over it being canceled in the past. So I think that that's one of the things that can kind of hurt the progress on it, is that, there's this enormous skepticism in the field that this will actually get funded this time around, because we've been burned before. But I do think it's important to learn to love again. So I encourage people to open their minds and their hearts to the funding of this. There's also maybe the biggest competitor for what we would be building in the future is what's called the FCC, so the Future Circular Collider. And likely this would happen at CERN. So what the FCC does is it's kind of a two-stage accelerator, where the first stage would be an E plus E minus machine, so electrons kind of like LEP, but now going up, instead of that 200 GeV number of LEP, going up to about 350 GeV, 500 GeV maybe, in that regime for E plus E minus. So the goal of this is just to produce Higgs. The Higgs is a really interesting particle. It's the only particle of its kind in the standard model. So studying it to absolute depth, I think, makes a lot of sense as a physics program, because it can tell us a lot about nature that we don't already know. So that's kind of the first stage of that, is going to study the Higgs a lot. And then it would shut down, they would revamp it, and then come back online a while later and produce the FCC HH. So that's the Hadron-Hadron Collider. And the goal of this would be colliding protons up to 100 TeV. So again, that sort of 100 TeV number. But again, because protons are composite, you eat another factor of 10. So really that would have a comparable energy reach to a 10 TeV muon collider. So, the arguments that people make for this machine is that, well, we already know how to do it, which is not to be ignored. Higgs physics is interesting, which I think I agree. And that the 100 TeV frontier, really the 10 TeV frontier, can be kind of reasonably reached. But of course, we talk about this like it's a done deal, but of course, there's lots of other things that can get in the way of this progress too. So I don't think the timescales for the FCC EE, so the E plus E minus collisions coming online, is actually that much before the muon collider. It might even come afterwards, because CERN has to finish its current program with the LHC before we would start building that.
Yeah, there are a lot of years left in the LHC's
a lot of years.
lifetime, the high luminosity run and everything that will go on for a long time.
Yeah, we're projecting that will go all the way up until about 2040-ish at this point. So it doesn't give you a lot of room to build a collider and turn it on before the same sort of timeline of a muon collider.
Might as well start on the muon collider now.
Might as well start on the muon collider now. Absolutely. Thank you, Dan. And of course, there's just straight up politics that make this hard. In order to make this happen, they need to dig 100-kilometer in diameter tunnel. And that's very big. So the only way that they can fit it and have it connect onto CERN is actually going under a lake and kind of through a mountain. And, it always cracks me up that some of the most expensive parts of having colliders is just digging the hole to put them in. So this would take a while. This would be involving multiple governments because this hole is going to span over a couple countries, and things like this. So, we figured out how to accelerate protons, and that's awesome. But it's not, a sealed deal either. So of course, what would I like as a young person who has absolutely no money is I want them both. Of course I want them both. I want to see Higgs precision physics and an E plus E minus, and I want to see a muon collider reach the energy frontier. Like, that'd be awesome. I want CERN to survive. I want Fermilab to survive. I want to do particle physics for the next 1,000 years of humanity, right? So I really don't like the rhetoric where people try to pit these machines against each other. For me personally, though, if we only get one, I'd love to see a muon collider.
A big thank you to Cari for coming on our show today. If you want to learn more about the science of particle colliders and all the best ones we already got, you can check out episodes 51 and 52 of our show. Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.